Hello, everyone. What I want to do now is talk about arithmetically decreasing annuities, and we'll do an example to show where such annuities appear fairly naturally. So the situation is basically the reverse of arithmetically increasing annuities. So let's say we have n periods and we have payments starting at NP for some P and ending at P. So let's say we have a per period interest rate of J as usual. So the timeline is as follows. The first payment is NP. That accrues n minus 1 periods of interest. This is an annuity immediate we're going to first talk about. So the first payment is at the end of the first year, and hence it accrues n minus 1 periods of interest. The next payment is n minus 1p. That accrues n minus 2 periods of interest, etc., etc. The second to last payment is 2p, and that accrues 1 period of interest. The last one is P, that accrues no periods, that accrues no interest at all. And so if you add all this up and do a little bit of algebra, you're going to get the following formula. D is for decreasing. So the accumulated value of a decreasing annuity, where the first payment is NP, then it's n minus 1p all the way to P, is just P times n1 plus j to the n minus snj over j. And the way you should think is it just happens to be that, just algebra, basically, just basic algebra says this is what it's going to be, or basic, manipulations with finite geometric series. Okay, and if we have instead an annuity due, so basically it's the exact same timeline, just literally everything shifted over one period. So the payments start at the payments start at t equals 0. At t equals 0, you have a payment NP. At t equals 1, you have a payment n minus 1p. And at t equals n minus 1, you have a payment of p. It's the exact same formula, except, well, everything just accumulates one more period of interest. And hence, it's the exact same formula, except you multiply by 1 plus j. Okay. Yeah, which is as usual, if you think about it. The only difference between the accumulated value of an annuity immediate and an annuity due is that in an annuity due, everything accrues one more period of interest. Right, and the present value, multiply everything by nu to the n, same thing as 1 plus j to the minus n, and we get the present value of a decreasing annuity immediate is p times n minus anj over j. And again, just multiply by 1 plus j. You're basically discounting everything by one less period, which is the same thing as multiplying by 1 plus j. And you have the formula for the present value of a decreasing annuity due. Okay, so yeah, let's do an example to illustrate where these formulas pop up and why this is an important thing to study. Okay, and this is very similar to a former actuary problem, and similar to 2.3.13 in the book Broverman, as usual, Broverman, Mathematics of Investment and Credit. And this is going to be similar to a homework problem I will assign. So you invest $10,000 into an account earning 4% effective annual interest. You withdraw interest, and in addition to interest, you withdraw $2,000 at the end of each year into another account earning 5% effective annual interest. And if it's not clear, if the context is not clear here, you're withdrawing that year's interest. So you're withdrawing 2,000 plus that year's interest at the end of each year. So find the, and sorry, when I say you withdraw into another account, I mean you're withdrawing and then depositing that amount. You're depositing the year's interest plus 2,000 into this other account. So when I say you withdraw into, I mean you're withdrawing and taking that and depositing it into the other account. So find the accumulated value in the second account when the first is depleted. Okay, so yeah, I definitely would draw a timeline here to basically get an idea of what the hell is going on. So this is another example where you cannot just plug and chug. Maybe you can just plug and chug into your head and figure out exactly what's going on in your head without time diagrams, but I don't think most people can. So, right, let's draw a time diagram. So first of all, let's draw a time diagram for the first account, which is not very subtle, but in case there's any issues or we're not all on the same page here, so total and first account. Okay, so right, let me just start off here. I don't know, it's not hard to figure out when the first account is depleted, but right off the bat, I don't quite know. So I just know that there's an initial 10,000 deposit. Okay, and I know at the end of the first year, I'm withdrawing interest, whatever that is. We don't care right now, but it's interest plus $2,000. So that just means you're just chipping away at the principal 10,000 by 2,000, which means you have 8,000 at the end of the first year. Okay, now let's do this again. Whatever interest is earned from year 1 to year 2, you're withdrawing that and an additional 2,000. So that means, well, you're just basically withdrawing, you're chipping away at this principal here, 8,000 amounts, and you're chipping away by 2,000. Okay, so just keep going. It's pretty clear that this is going to end. We're going to have the first account depleted at the end of the 5th year. This is 4,000, 2,000, keep subtracting 2,000, and 0. Okay, hopefully I can fit this. All right, so now this is going to be similar to, I forget the problem exactly, but we had like an increasing annuity problem, arithmetically increasing annuity problem that was kind of similar to this. So deposit, sorry for that, deposit, not deposit, deposits into second account. Okay, so, well, so at the end of each, at the end of the first year, I'm going to deposit 2,000 plus the interest earned in that year. So, right, I'm going to do this just like we did before. So we're depositing at the end of the first year. I'll draw the dots to make sure it's clear when things are occurring. 2,000. Let me move this over a little bit, make sure I have enough room. Okay, so let's ask ourselves, what is the year's interest? Well, this is not very subtle. In this account, in the first account, it earns 4% annual interest. So 10,000. So we just have 10,000 in the account. That earns 10,000 times 0.04, which is $400 interest in the first year. So it's 2,000 times 400. Again, you know what? It's 10,000 times 0.04. Okay. And we keep doing this. So from from year 1 to year 2, well, we have 8,000 at the beginning of year 1, and that accrues the interest earned in the second year from year 1 to year 2, or from the end of year 1 to the end of year 2. Well, it's 8,000 times 0.04. It's 4% annual interest. 8,000 sits in the account for 1 year. So you you deposit the 2,000. And again, it's, 8,000 times 0.04 is just 320. Okay. And you just repeat the pattern. So I'm gonna have to squeeze this in, but I think I can do it. So it's 2,000 plus 6,000 times 0.04, which is 240. Okay, and I gotta make that a little smaller. So actually, let me put this here. And yeah, just like here, I'll just write it 6,000.04. So this is 2,000 plus 4,000 times 0.04 is 160. And it's 2,000 plus 80. 2,000 times 0.04. So I think I can fit this in. It's 0.04. Maybe make the 0 a little more readable. But anyway, hopefully, yeah. Okay, so right. So basically now it's kind of, well, based on this timeline here, it should be relatively clear what's going on now and how to apply our formulas. Anyway, so yeah, just sorry about this. Just putting the red dots again in case there's any kind of confusion when these payments. I guess I could just circle this. It's probably a lot more efficient. I'll do that in a second. Right. So this is the amount t equals 1 in the second account that we're depositing. This is the amount t equals 2 we're depositing, and so on and so forth. Here we go. Okay, so it should be clear that we have basically 2 pieces here, and that's why I'm writing it as 2,000 plus 400, 2,000 plus 320, 2,000, 240, et cetera, et cetera. So we have our just plain vanilla annuity immediate. It's annuity immediate because this is at the end of the first year, second year, third year, fourth year, and fifth year. So we have just a 2,000 deposit. And then we have our arithmetically decreasing part. So that looks too much like the blue. So let me, I don't know, orange is as good as anything. And so if you think about it, this is exactly the situation of an annuity. Get rid of these. These are kind of annoying. Yeah, so we're in this annuity, we're in this arithmetically decreasing situation here. N is 5. P is fairly, well, P is, and P is always going to be the last payment. I'll fix that in a second. So in particular, P is 80. And so you should definitely just check that, just check that this fits the pattern for this arithmetically decreasing annuity. It's 80, 2 times 80, 3 times 80, 4 times 80, 5 times 80, where 5 equals N. So it's P, which is 80, 2P, 3P, 4P, 5P, which is the same thing as NP. Okay, so, right, so with all that, the accumulated value, in the second account, well, like I said, it's your plain vanilla annuity, plain vanilla accumulated value of an annuity immediate, 2000 S5.05. So again, before I continue on, I just want to emphasize that just like when we did the similar problem with reinvestment, the similar reinvestment problem, the 4% for the first account has no relevance to our annuity formulas for the accumulated value, for finding the accumulated value in the second account beyond telling us how much is deposited into the second account. That's all the 4% is needed. That's all it's needed for. It is just needed to tell us how much is deposited into the second account at the end of each period. Okay. For the annuity formulas, what's relevant is this 5% that the second account earns. So with that in mind, let's go back and finish up this problem. So it's 2000 S5.05 plus, again, as we said, our P is 80. So 80 DS. It's an annuity immediate because, again, so maybe I'll just draw dots here, or maybe you should think this is kind of nothing here. So yeah, payments start at the end. Payments are at the end of each year, end of the first year, second year, third year, fourth year, fifth year. So immediate annuity, immediate situation. That go back. What am I doing? Go to the right. So it's annuity immediate. So DS5. .05. Okay, so yeah, I guess I can just do this real quick in the calculator. So second clear TVM. So 5N, 5% interest, 2000 payment. Again, doesn't matter, as I said many times, plus or minus. If you put plus, you'll get a future value of minus. So this is 11,051 and 26 cents. All right, so let's do, whoops, sorry about that. Let's do this here. So just plug and chug. It's 85, 1.05 to the fifth minus S5, 0.05, another parentheses here. This whole thing here over J 0.05. Right, so yeah, not that I really need to do this, but yeah, so for this one here, n equals 5, p is 80, j is 0.05. Okay, right, so I'll just show you how I would do this in the calculator. I would probably, well, like I mentioned before, I would probably use the TIX, I forget the name of it exactly, see if I have it here, somewhere on my desk. It's the TI XS multi-view, I think. But if you do want to use this calculator, what I would do is I would first get this here, S5.05. That makes life a lot easier. Okay, so 5N, 5% interest, 1 payment. As usual, there's nothing here, so it's 1. Or if there's nothing here, that means the payments are 1. Compute future value. Okay, so what I would do is make this minus. I would add it to 5 times parentheses 1.05 close parentheses to the y squared, y to the x to the fifth, so that to the fifth, which is the yx here. Yeah, it drives me nuts not being able to see what I'm really typing in. So the thing I don't like about this calculator, I always have this kind of little panic in my mind, like, you know, is this going to come out correctly? I can't see what I'm even entering. So, yeah, and this comes out, this is correct. So that's the order I would do things. And yeah, more parentheses, the better. So yeah, anyway, this whole thing here is 1369.24. So I should say equals here. Get rid of this. So 1151.26. 1369.24. And so your answer is 12,420 and 50 cents. So yeah, I definitely like these problems. I mean, this is, I like this problem because it's fairly realistic, and it tests that you understand what's going on here. Once you understand what's going on here, and remember, like I'm doing, to write it like this: 2,000 plus 400, 2,000 plus 320, et cetera, so that it's immediately clear that you break this up into 2 annuities, one with this constant level payment of 2,000, the other one, this decreasing annuity. Yeah, so once you do that and understand everything, it's just plug and chug. Okay, anyway, enough of that. So I want to finish this video up with A problem I could have assigned in the last homework, but well, there was enough homework there, so do it now. And it's a good problem. Again, it's you can't really plug and chug for this one. So we have the following situation. I'll draw a time diagram if it's not clear exactly what's going on, or I'm going to state this a little too fast. So we have the situation here where we have deposits of 100 per period. Okay, that's it. So we have an annuity that lasts n periods, and each period, or at the end of each period, we deposit $100. So I don't think I make it clear in here if it's at the beginning of each period or at the end of each period, but it is at the end of each period. I would make clear on quiz, exam, or homework. And we want to figure out when this accumulates to at least $2,000. The first time it accumulates to at least $2,000 if 10 deposits, or if for 10 periods we have the first 10 periods we have 5% interest, and then after these 10 deposits we have 6%. We're followed by n deposits at 6%. Okay, so let me draw a time diagram if this isn't 100% clear. Whiteboard. Okay, so the timeline is as follows. So, yeah, as I mentioned, everything is $100 deposits at the end of each period. Okay, so we go all the way up to 10. And so per period interest for the first 10 periods, as I said, is 5%. Okay. And I'm going to put it like this. We're looking for the smallest n where we have an accumulated value of at least $2,000. So from 11 onward, or rather from 10 onward, J is 6%. Let me make that look like a J. There we go. Okay. Right. So let's break this up into two annuities. So yeah, this is, oops, sorry, it's not 10, it's 100. So I'm going to break this up into two annuities. That's what you have to do when you have an interest rate change. So let me first do the annuity from, let me do this annuity here first that I'm going to circle in red. Okay. So I'm going to do this annuity first. Okay, so, right, so this is 10 plus n. This is 10 here, 0, 1, 2. And again, 5% interest here, 6% interest here. So 100, 100, 100. Okay, so nothing subtle here. 10 is annuity immediate, 10 periods, $100 payments at 5%. Okay, so this accrues, well, you have to be, I guess, a little careful. So from 10 to 10 plus n is n periods. I mean, that's pretty obvious, so don't have to be that careful. So this amount here, which I'll get in a second, S10.05, this accrues n periods of interest at per period interest rate of 6%. So it's 1.06 to the n. And this whole thing here is just to really fit it. And because I don't need to be that careful with how I round, I'm finding n. N is just going to be an integer. Oh, I'm going to find n and round up to the nearest integer. I'm just going to round to the nearest cent. And if you do round on quizzes or exams to the nearest cent for everything, that's fine. You will notice that you get answers that are off by a couple dollars, maybe even as much as $10 or so from, from the correct answer. But that's okay because I'm more interested in seeing that you understand what's going on rather than getting exactly the correct answer. Because on the job, obviously, you're going to use Excel to do these calculations. So yeah. Anyway, where was I? 74. Sorry about that. Little brain fart there. 1.06 to the n. So that's what this whole thing is. Okay, so let's go back real quick. And now let's do this annuity here. How does it matter? So maybe I'll circle this in red to emphasize that this is the accumulated value of this first annuity here. So let's do this annuity here. Yeah, and so this you have to be a little clever. You can't just really, I guess in some sense, some clever sense, it is plug and chug. Okay, so 100, 10 plus n. Right. So I don't know if I put I didn't put the dots here. I mean, not that it matters, but anyway. Okay, so, well, right. So here, 6%. Yeah, sorry about that. Okay, so as I said, 10 to 10n is n periods. So this is just 100. Well, this is just an n period annuity. Payments are 100. Annuity immediate from the time diagram. N periods, 6% interest. Okay, so the only problem is we can't just plug this into a calculator, even a financial calculator, because we don't know what n is. So what you want to do, and this is where you have to be a little clever here, is just write out the formula. 1.06 to the n minus 1 all over 0.06. Okay, and I don't remember what color I used, blue. So this is the accumulated value of the second blue annuity right here. Okay, and the reason why I want to do it this way is, well, lo and behold, I have a 1.06 to the n here. I have a 1.06 to the n here. Maybe I can do a little bit of algebra to figure this out. Okay, so let's first get the accumulated value, the whole accumulated value. So it's the first one, which we said was 1257.74, 1.06 to the n. So write that down. 1257, 74. whoops, forget that, 1.06 to the n plus, second one we just wrote down here, 100, 1.06 to the n minus 1 over 0.06. All right, so let's simplify this a bit. 1257. Can't really do anything to the 1.06 to the n. Let's just simplify this here. So 100 over 0.06 is $1,666.67. All right, so it's so yeah, distribute that between 1.06 to the n and the minus 1. It is 1666.67 times 1.06 to the n minus 1666 0.67. Okay, so we're trying to figure out when it has at least, right, so sorry, let me just simplify this a little bit more. So add these two up. It's going to be 2923, yeah, 0.67, 1.06 to the n. Minus 1666.67. Okay, and right, so maybe I'll do this in orange here. Right, so we're trying to find when this has at least 2,000. So like we did before, we set this to be 2,000, solve for n, and we're going to round up, and we'll check our answer as a sanity check. Right, so you add this amount here to both sides, and you're going to get, go do this here, 3,666.67 is 2923.67, 1.06 to the n. And again, I do like this problem because you absolutely have to know what's going on. There's just no way to just plug and chug. There's nothing to plug and chug into, really. Right, and you're going to get n, just divide by 292367, ln of both sides, divide by ln of 1.06, 3.886. So the answer is, rounding up to the nearest integer, n equals 4. Okay, so let's check here. So what are we even checking? Well, we got the, so I'll do this in green here, I guess. So this whole thing here is the AV, the accumulated value of the annuity. Well, what annuity? The whole annuity, this whole thing here. The whole thing I'm circling in green. So maybe at this point I should get rid of the, right, so this whole thing here, the accumulated value of the whole thing green is this here. Okay, so let's do a check. Let's first of all check that you do get over 2,000. You have at least 2,000 here. So, right, just plop in n equals 4 here. I guess I'll leave it in green, no harm there. 2923.67 times 1.06 to the fourth. Yeah, sorry, minus 16667. Sorry, 67. And you're going to get 18. Sorry, you're going to get 20. 20, 25, and 34 cents. Right. Okay. So you do have at least $2,000, and let's plug in 3. That you know, by doing that, we're checking that this is the first. You know, n equals 4 at the end of the fourth year is the first time, or at the end of the fourth period is the first time you actually have less than, you know, at the end of the first full period. This is the first period where at the end of this period you have over $2,000. At the end of the third period, you have less than 2,000. When you just plug this in, and you have 1816.41. Okay. Right. Okay. So, yeah, hopefully this was informative and helps with the homework problems I will assign today. And I will put one last video for annuities on annuities, geometrically increasing annuities, and arithmetically increasing annuities in perpetuity. Some homework there. I won't talk about decreasing annuities in perpetuity. That doesn't really make sense when you think about it. Yeah, anyway, so we'll talk about, well, so videos for loans and bonds and measuring the rate of return are all up. So the next video will be the last new video. Yeah, so long, take care, and good luck in today's quiz if you're taking it.